Well, this week is diffraction week, Fraunhofer Diffraction. We'll spend 2 classes talking about Fraunhofer Diffraction. Fraunhofer, great astronomer. We have the Fraunhofer lines named after him in the solar spectrum. Although he did not work out the calculations for Fraunhofer diffraction, but we honor him by referring to this kind of diffraction as Fraunhofer. Basically, it means you're going to be far away from the slit or the sources of the light where you have little openings. Generally, diffraction can be thought of as light spreading out through a small opening. And I'm going to look at sound here as an example. If you were to say hello to someone or come back after they have gone around a corner or went down the hallway, they would still hear you. In other words, you can say hello or come back, and the sound's going to get around the corner or through an opening. Or, for example, around a tree. If there's a tree in front of you, say hello, someone's going to hear you on the side. And a general rule, simplified, is that if the wavelength is comparable to the size of the obstacle or opening, you're going to get the spread out effect. For sound waves, trees and doors and corners that we encounter in real life are comparable to the wavelength of sound. But for light, since it's such a small wavelength, it's not going to go around the door. You can't see someone around the corner. You can't see light if it goes, if a flashlight and you aim it at a door, it's not going to go bend around, go down a hallway like the sound waves will do. If you say hello, come back, someone can hear you after they went out the door. So for light being such a small wavelength, you would need like a razor blade, slit to get the diffraction effects and interference effects. However, next week, when we look at Fresnel diffraction and close range, we'll see that fairly large objects can be involved, or openings, to get some interesting effects with diffraction at close range. The Fresnel so-called near field diffraction. So with Fraunhofer, you can think generally in a laboratory setting that the screen is far away from the slit and the laser source. So this is a very fascinating area. We see nice mathematics. We bring in the Laplacian, and we actually can touch base with the Fourier transform, since the integral that we're going to get the pattern on the screen is very similar to Fourier transform. In fact, it could be considered a Fourier transform. So when you have your source of light coming through, say, a little rectangular slit, that the Fourier transform is on the screen. Fascinating stuff. And finally, I'll mention that basic properties of light for the whole course: reflection, refraction, which we have done with the Fresnel equations, for example. Now diffraction and interference. And if you add polarization, we did polarization. So these are like 5 characteristics of light. And then when Einstein comes along and says light's a particle, the photoelectric effect, that kind of throws a real confusion into the mix. But let's not do that now. We're actually at the situation here where we're looking at light as a wave, physical optics, and we will not consider the photoelectric effect at this point. All right, wave optics for the next few classes. Chapter S, Fraunhofer Diffraction. Let's look at S0 and talk about waves in general and their properties. First, we have reflection. These are the big 4 I'm going to show you that I teach my non-science majors. And if we use here the the angle of incidence will equal the angle of reflection. And we could have air and glass. We use light as an example. But all waves will experience this. Then refraction, where if we had air and glass and put our normal in again, the light bends toward the normal and you have some reflection. Now the topic for today, diffraction, if you consider here, like in water, these two barges, and here are waves coming in, then if the wavelength, these are your crest, if the wavelength is comparable to the size of the open, say D, then the waves will spread out, diffraction. And you could hear someone, like down the hall, if someone shouts out at you, since the sound waves are comparable to the size of doors. Now, if the wavelength is very short, like really bunched close together like this, then pretty much going straight through. And this is why you can't see someone around the corner, since light waves are really short wavelengths compared to like door sizes. Then interference. We've talked about interference a little bit before. Here we have two openings. Then when the crests overlap, like here, if you look straight in the middle of a crest overlap, trough overlap, crest overlap. So basically you get a bright region here, and then when a crest and trough, one of each are overlapping, they cancel. You get dark, and then here, overlap again here, then you get bright. And we'll be looking at this today also when we do two slits. We could add here polarization. And here the polarization would be in the plane of the paper, vertical polarization. And if we were to have something like this, in and out of the page, sometimes just go put a dot there. So mixed polarization would be given like this. And we saw the law of reflection derived from first principles, the Fresnel equations, and refraction also. And now we're going to look at some fundamental treatment, these others. So before we do that, let's relate this to the Laplacian spherical waves and the wave equation, del squared on psi is 1 over c squared, second derivative with respect to time. Now the Laplacian, which we derive in spherical coordinates, 1 over r squared, d dr, r squared, d dr. These are partial derivatives, plus 1 over r squared, sine of theta, partial with respect to theta, and then finally, for the third dimension, the phi. Now we're going to look at a situation with spherical symmetry, so that if you look at, say, the wave, which in general can have x, y, z, and t, which you can write as a vector form. Sometimes you see that form, sometimes you see x, y, z, t. And we're going to look at a case where we just have the r and t. In that case, since the psi does not depend on the angles, these are gone. And the Laplacian, for our purposes, is just the r part. So what we're going to do now is we're going to try to solve this equation. And let me go ahead and write down everything here. 1 over r squared, partial with respect to r squared. And we can put the psi in there. Is 1 over c squared, second derivative with respect to time. So what we're going to do is try for a solution. We're going to take an r function of r, just say, call it capital R, divide it by r, and e to the minus I omega t. Now I picked this because when you have the inverse square law, like when you square the amplitude, you get 1 over r squared. You get an inverse square law. So I'll go ahead and put that specifically, in this form, so that when you take, psi star, when you're getting the for the intensity, that's going to become, this will go away because a star will make that a plus. When you multiply, it'll go away. So you'll basically have something proportional to 1 over r squared. So we want to put this thing in the differential equation, the partial differential equation. So let's do that. 1 over r squared d dr. We have r squared d dr, and we're going to have in here the r of r over r e to the minus I omega t equal 1 over c squared, second derivative of the psi function. Okay, there you have it. Sometimes this is referred to as the separation of variables technique, where you separate variables. In this case, we are justified. Of course, time and the r are going to be independent. So in that case, we can see that the time dependence can be filtered out here. 1 over r squared. And we can make these regular derivatives now. R squared d dr and over here we can pull out the r dependence, and this becomes a regular derivative with respect to time. Over here, two derivatives will pop the I minus I omega down twice and give us the same thing. Now remember this formula. Remember the formula that omega over k is equal to your speed, all right? We have one wave in vacuum here, no group velocity just the omega over k standard form. So therefore, over here, you're going to have an omega squared over c squared on this side. So omega is ck. So when you have the omega squared over c squared, omega over c is just going to be k squared. So you're going to have k squared over here. So you're going to have this formula where this time dependence will drop out, and we can replace these constants with just a k squared over there. Now you could, in terms of the r and the t, these are all constants. Okay, so then we have 1 over r squared ddr r squared ddr capital R over r. And I'll leave out the explicit expression of the argument. Now here, let's see, minus I squared is a negative, so this is going to be a minus k squared, and then r over r. So let's go ahead and work on this. We can do a couple things here. First, we can take one derivative here using the product rule. The derivative of the first is the r prime, keep the second one the same. And then the derivative of the second would be minus 1 over r squared. And we can bring this k squared on the other side like this. Now we're going to go ahead and multiply in here. Let's go ahead and do that. This is then ddr. This will be little r times big R prime, and then minus big R plus k squared big R over r. And then we now go ahead and take the next derivative. And that would give us here derivative of the first just be a 1. So this is an r prime plus the little r times then the derivative, second derivative, minus r prime plus k squared big R over little r equals 0. Now here, this is nice, that cancels out. So we have r prime, double prime, second derivative, and then one of these r's will drop out, plus k squared big R over r equals 0. The r's drop, little r's drop out, second derivative plus k squared r equals 0. So what we're looking at here is we're saying the second derivative of the big R equals minus k squared, and the big R comes back. Well, we're very familiar with that kind of a situation, because if we take, sines and cosines, does do this trick. So here, say this is a e to the I k r, and you can even put plus or minus there, like the wave traveling in either direction. And then if we look at all of this, our solution is going to be, we'll say here, we could have the a e to the I k r, e to the minus I omega t will be in there, and we'll be dividing by r. So we can say that we have like some constant here, e to the I k r minus omega t over r. So that's the general idea. And we may, I sometimes call that C, capital C. And let's do that. Okay, so let's go on to S2. This would be the Huygens, Fresnel principle. And Huygens Fresnel principle is that you can make waves, the future waves, by replacing waves, say, by baby waves. So we put little baby waves here like this. Then see, here would be the future wave. And we'll have to suppress waves going backwards. We'll talk about that in another class, but this is the general idea of things proceeding forward. So really, here, the baby wave, say it's going to be a spherical wave, the baby wave is going to be, I'll say, I'm going to use C here as a constant, e to the I k r over r. And that has the property of the inverse square law. You know, if you look at the amplitude times the amplitude complex conjugate, you're going to get 1 over r squared. So here's a picture of Huygens and Fresnel we've already encountered. Christian Huygens and Fresnel. There they are. So if we look at this picture that shows here the baby waves, these are points here. So here's that plane wave coming into an opening, like I did earlier for you, showing you. You have the baby waves, and you then have, look, you have C interference going on in here because the baby waves are interfering. So we'll get light and dark just for having one opening diffraction. So in this model here, you don't get bright and darkness. This is a little too simple. Here you can get interference, but even here, you're going to get bright and dark regions. You're going to have the baby waves undergoing interference. So we go to S3, Fraunhofer Diffraction. They named this after Fraunhofer, although he didn't develop these equations and this treatment, but he's such an important figure in physics and astronomy. And here is a picture of Fraunhofer, physicist, astronomer, inventor, lens manufacturer, and invented the modern spectroscope, where you study light coming in like a prism action, like separates out the colors. And here, these are absorption lines in the solar spectrum, Fraunhofer lines. He worked a lot in this field called spectroscopy. So the idea then is to integrate this. See, when you add up all the baby waves, you're basically doing an integral. And that's what we're going to be looking at next. We'll be doing the single slit first. And you can think of this as some point away from the source is going to be an integral. We're going to integrate over the aperture or the source region, say E naught EIKR over R dA. So this is the whole idea of what we're going to do. We'll be doing a few problems today, and then we'll do some next class. All right? Fraunhofer diffraction. S4, single slit. Now I'd like to sketch this where the light's going to come in from the left, and this is going to be our slit, our diffraction. But here, if I draw a picture, if you were to like look at this thing, it goes like down. In other words, what you're seeing here is the width B. So there is B, but then in the other direction it has a height like this. All right. So that's the general idea of this setup. Then if we look at a larger version of this, this would be B over 2. If we put the origin, say, in the middle, negative B over 2. And this is B. And your height is like in the other direction, like into the page or come out of the page. All right, so there's the origin. And we're going to look at here a point down the bottom. And we're going to look at comparison, the optical path length. This here is the extra distance, and that's important because if a crest leaves here and if the crest leaves everywhere, say the same time, but then if this here is another crest, then they're going to reinforce in that direction. Just like we had the simpler diagrams earlier. This is more now advanced, and this is U. This is 0 is U. U is going to be integrated from like minus B over 2 to plus B over 2. So this extra path is U sine of theta. Now the theta is the angle in here, and we should enlarge things so we can see better. Okay, here is U, here is theta, and this here is theta also, since that's a right triangle, and since this is a right angle and that's a right angle, these are complementary and these are complementary. So we're going to take this to be R naught going along the axis, and that's going to be very, very large. And then here, this is going to be approximately R naught. So these are going to be approximately R naught, but we got to be careful that down here, we're going to add the U sine of theta. Now, if you go very, very far to the screen, you're going to have over here some X away from the center, and the sine of theta will be approximately X over R naught, because these are both going to be approximately R naught when they're very, very far away. So that helps relate to geometry. But we're really interested in doing the integral. So we're really interested in taking, there's a point P out here on the screen, and we want to integrate over all these that are going to head over to point P. So that would be then the integral over the aperture, E naught, that's our constant here. Before we call that C. And we're going to look at this integral. And here the area is going to be the height in that other dimension times du. Right? That's going to be the area that we're looking at. So the total area there is going to be h times b, but I need to use the u variable because I'm going to be integrating in that dimension because things are going to be changing. So you can think of this as a du and then you go into the page for your h. So we're going to integrate this out. I mean, if you were to draw the picture like this, where this is your h, then your u is going to be in this dimension. So you could imagine here having a delta u strip. Like, see, here's a delta u, and then multiply by the h, that gets you the area. But then you have to turn this sideways like this. So just think of here delta u, and then h in the other direction. So we're good. But 1 over r is going to be approximately 1 over r naught. Now we can't make that substitution up in here because these are sines and cosines, and they're bounded by 1. They're going to oscillate. But see, we can do it here because when r is large, I mean 1 over a large number, I mean this is going to be pretty much, you can neglect that if you're looking far away. So it's okay to do it there, but not up in the exponent. So now we have EP is E naught H over R naught. I integrate from minus B over 2 to plus B over 2, E to the I K, and now I put in here the R naught plus the U sine theta. And now you can see that the integral that has a u function in there. Let's go ahead and call the E naught over R naught capital C, so we don't have to write down so much. I'm going to keep the H there though. Minus B over 2 plus B over 2. And this is E to the I K R naught times E to the I K U sine of theta du. Now this can pop out. There's no u in there. So then the electric field strength at the point on the screen, this is the point P on the screen far away, CH E to the I K R naught integrate minus B over 2 to plus B over 2 E to the I K U sine theta du. Now we can look at this integral and write E to the I K sine of theta together and have the u out there to the far right. So when we do that, we can do the integral. We're going to get e to the I K. This is exponential, so these are nice. All this times the u over I K sine of theta. We go from minus b over 2 to plus b over 2. I like to check my integrals by going backwards, take the derivative. If you take the derivative of this, you get the same thing back, but using the chain rule, you're going to pop out whatever's in front of the u, which will cancel that. So it checks out. It's correct. So that gives us, for the electric field at that point, we have CH E to the I K R naught over I K sine of theta. And now comes the fun part where we put in B over 2 for the U. And then we subtract and put in minus B over 2. So this would be minus IK sine theta B over 2. And now what we're going to do is take this combination K sine theta B over 2, and we're going to say let beta equal 1/2 KB sine of theta. So that is going to simplify things up there. We're going to have, in that case, EP CH e to the I K R naught over IK sine of theta. We'll have the exponential, we'll have an I beta minus e to the minus I beta with that definition. But now you can see that, see, this is 2I times the sine of beta. Always remember your Euler, your sines and cosines. So if that's the case, then these i's will cancel. And we'll have CH, now e to the I K R naught. And this will be here K sine of theta. There'll still be a 2 floating around. And there'll be a sine of beta. Now I can do a little trick and get this 2 down in the denominator, because I'm seeing I got a K sine theta, I got another beta here floating around. So watch this. I'm going to put a B here also. I'm going to put a B up there so I can put a B downstairs. But this 2 I can put in the denominator by have 1 over 2. And now I can see that this part here is another beta. So that means EP is CHB e to the IK or naught sine beta over beta. Hey, that's the sync. You might remember that when we took the Fourier transform of a box, we got the sync, like the pulse. This is in a sense like that, a rectangular pulse, like where you have a region where you have brightness, and then this is very similar, this exponential, to the Fourier transform idea. So you're seeing the Fourier transform here at the screen. That is wild. And I like this, see, HB showed up. That's the area of the slit, the total area of the slit. Nice. So here, if we want to find the irradiance, remember that's 1/2 times the EP, the amplitude squared, but since it's complex, we do the Z star idea. So this is 1/2. And when you do this, you're gonna get a C squared and A squared, but then this e to the IK R naught will have then a minus sign because of the star, but all the real parts get squared, and this becomes 1. So what we get here for the irradiance is 1/2 constant C squared, A squared, sine beta over beta squared. Now remember, when beta goes to 0, this is your sinc function here. That's going to go to 1. And when beta goes to 0, remember beta is 1/2 KB sine theta. So that means, 0, you can think of here as like when theta, see, the logic is we're trying to figure out to get this in terms of I at 0 degrees, the central brightness. So we're saying that if you want theta to be 0, then beta is going to be 0, and this is going to be 1. Well, that means this has to be the intensity at 0 degrees. So we got it. I is I, we could say I naught. That's when the theta is going to be 0. And this is going to be, we can write this as the sinc square root of beta. That's it. That's what happens at the screen. So here we have it. You can write it in these fashions like this. And here is a plot showing the central brightness. And now look, you get max and min on either side from the calculation from first principles. So constructive and destructive interference. So let's look at where the minima may occur. Well, the minima, that's going to be easy because that's going to be when the sine of beta is going to go to 0, except for beta being 0, because with L'Hopital's rule we showed that was 1, but say for beta not equal to 0, but the other places. And that's easy because that's going to be, the sine is going to go 0 on us, that plus or minus pi, plus or minus 2 pi, and etc. So let's consider this looking at the analysis for the minima. And that's going to occur when the beta is plus or minus pi. Now remember, you just have to be careful that the beta is equal to a function, of the theta. So when this is plus or minus pi, then you have to go in and find, what the actual angle is, this angle here. Now the maxima, because see, here's a maxima there, there's one there, of course the central maximum there. That one's tricky because for that one, if we do our derivative, say d beta on the sinc function, and set it equals 0, okay, then we have minus 1 over beta squared times the sine of beta. This is taking derivative of the 1 over beta first, and then plus the 1 over beta, and then the derivative of the sines of cosine equals 0. And then you get here that the sine of beta over beta squared equals the cosine of beta over beta. And that means the tangent of beta, if we bring the cosine over and throw that b squared to the right, you get this equation. That's transcendental. Transcendental equation. Wild. I remember first seeing that in quantum mechanics. The finite square well. You'll probably see it there. So we use a graphical technique to solve it. In other words, when you have a tangent of beta is beta, you have, think of it like this. Just go ahead and say tangent of x equals x. Then you have the equation y equals x and y equal tangent of x. And if you graph both of those, where they intersect, like they're the solutions, they're the points for the solution. So here's y equals x, and there's your tangent. It goes from 0 to infinity, pi over 2, and it starts over again and over again. So you'd have a point here that would be at the central maximum. Then there's a point there, and a point there, and a point there, and these would be your cases that you would get the various maximum. So the central maximum, and then here's a maximum, and there's a maximum. I think it's cool to play around with the calculator, that if you have, say, you want y equals x and y equal tan x, if you look at the solution that we had over here, you can see that this, if that's the zero solution, or if you want to consider the central maximum, then here's the first one off to the side. And you're looking at, this is 1.5 pi, this is pi, so that's kind of like 1.4 pi. So if you take that, and then over here, this is 2.5 pi right there, 2.5 pi. So that's like maybe 2.4 pi. So I'm playing around with this. And if I take here 1.4 times pi, I get this. Well, I don't actually get that. Actually, you get close to this. These are the exact solutions for Wolfram. And then here, if you take the 2.4 pi, but at first I just got close and then played with my calculator instead on radians, and like hit it with the tangent and hit it with the x, and it was fun just guess and get closer and closer to the next significant figure. But the easiest way, of course, go online and just have Wolfram do it for you. So there's the plot here of the sink squared, because you want to square the thing for the irradiance. And you're going to have your minimum. So this is going to be at pi. It's at 3, a little more than 3, pi, negative pi, and then here 2 pi is going to be a little more than 6. That's going to be there. So you can see it all here. It's nice. And we use the graphical solution to get the maximum case. That's 5. The double slit. And here's where the interference will kick in again. All right, where you have the 2 slits. So double slit, which I sketched easily without any details before for you. Where we had the waves coming out. So now we're going to pick down here to be the 0 points, easier for the integral. And then you're going to go up to B. This is size B and B. And let's say that the distance between the slits is A. So if I shift this down a little bit to consider this point and this point, that's also A. Just shift down by minus B over 2. So really, I'm all set. It's time to do math, because we have this case. We had this case before. Let's just go ahead and review what we had before. E to the I k r naught plus u sine of theta du. And we're going to adapt this by, instead of integrating from minus b over 2 to plus b over 2, we're going to go from 0 to b. And then we're going to have a piece to go from a to a plus b. Let's put this c and this h on the left side. And we integrate from 0 to b. E to the I k r naught plus u sine of theta du. And then we integrate from a to a plus b. E to the I k r naught plus u sine theta du. And we're going to pull out the e to the I k r naught. And if I put that on the left side, it goes in here as a minus I k r naught. So I'm pulling the I k r naught out like we did before, and just get it on the left side so I can clean up the right side. So then I have the integral from 0 to b, e to the I k u sine theta du plus a to a plus b e to the I k u sine theta du. Now these integrals are easy to do. This one's going to be e to the I k. Now we'll have a u here. I'm going to put the u on the far right. So this integral, we have the same thing, and then down here is I k sine theta, like we did before. So we take the derivative of this thing, you get the same thing back, and the I k sine theta pops down, cancels. So that works. That's from 0 to b. And then over here, we're going to have e to the I k sine theta u again, same, and the limits a to a plus b. Okay, so now I'm going to take this, the EP over to CH, e to the minus IK R naught, and I'm going to bring the IK for the moment to the left-hand side so I can concentrate on these exponentials. So let's move that over to the left-hand side. So I have e to the IK b sine of theta minus, when you put the 0 when you get the 1. So that takes care of this first one. And then the second one here is going to be e to the IK a plus b sine theta minus e to the, now here you gotta be careful, this is not a 0, this is an a. So that's gonna be IK a sine theta. You just put the a in there. That's all you have to do. So here you have the a plus b for the u, and then you have the a for the u and the minus sign. Here you have the b for the u, and then here, because it was 0, you just have the 1. I'm going to factor out on this one. Since I have a ka in both places, if I take the IKA sine of theta, I'll have here e to the IKB sine of theta. So if you multiply these two, the a and b are going to add in the exponent. So you get that, and then minus IK sine theta. So you can see this is the same as this over here. So that means we can write IKA sine of theta e to the IKB sine of theta minus 1. But see, that is the same as that over there. So now we have a big time, factoring that we're going to do. And we'll go ahead and write everything out again. So EP, CH, e to the I minus KR naught, IK sine of theta. So we're going to then write this term first, e to the IKB sine of theta minus 1. So when you factor this out, we're going to have one of them. That's this one here. But then over here, we're going to have a plus because of this plus sign. And we're going to have this thing here, KA sine of theta. So this came out front, and then we have one of them here, and then we have this factor for the other piece. Now watch this trick. If I pull out IKB sine of theta, say over 2, Then I'll have an E I K B sine of theta over 2, because when I multiply these, I'll get one of them in the exponent. But then here, to get that minus 1, I need a minus I K B sine of theta over 2. And then over here, I have the 1 plus e to the I K A sine of theta, same thing. So the reason why I did that is because you see a sine is coming out of here. Using the Euler relation, this is going to be 2i times the sine of kb sine of theta over 2. And now if I look at this part and play a similar game, e to the I K A sine theta over 2, I'll have an e to the I K A sine of theta over 2 plus an e with the minus sign. Let's check this to make sure we're good. If this comes in here, you'll get a half plus a half. We need a minus sign here and a plus sign there. So when this comes in, the plus sign and the minus sign will cancel and you get your 1, because it'd be e to the 0. And then here, these two halves will add, you get 1. So now we're good. But see, this is 2 times the cosine of Ka sine of theta over 2. And now it makes sense to call that alpha, call that beta, like we called that beta before. And now all this mess starts to look really compact. EP, e to the minus I K R naught over CH I K sine of theta. So that's the left-hand side. So now on the right-hand side, I'm going to have e to the I K B sine theta over 2. Well, I should have just said that's a beta. So we could have simplified that, but that's okay. All right, and then here, 2i sine beta. So really this here is e to the I beta. Would have been better just to do that there. And then over here, this is e to the I alpha, and this is then 2 cosine alpha. Okay, let's go ahead and write this out now with the EP on the left. And I have the CH, going to bring it over to the right-hand side, and we'll divide by IK sine of theta. And then we have e to the I KR naught, that comes over. And then we have e to the I put the alpha one first, and then e to the I beta. And then we have 2 times 2 is 4, I cosine alpha and sine beta. All right. Now we see that we got another beta coming here. We'll do our trick we did before. EP we'll go ahead and watch this trick. We'll put a 2 upstairs, a CHB, and then here, let's cancel, let's go ahead and cancel that I while we're at it. That I goes off. So we have 2 CHB, so I have KB sine of theta over 2. So that's how I get my 4. 1 over 2 flips to get 2 times 2. So this is almost finished. IKR naught, e to the I alpha, e to the I beta, cosine alpha, sine beta. Let's just double check. Check, check. I's canceled. Check, check, check. And what about that 4? Well, here, when that 2 comes back up, you'll get the 4, and the betas cancel. Everything's looking good. And we did that because, see, this is a beta. And look at that, you get your area again, isn't that nice? H times B is the area. What is that area? That would be the area of one of the smaller openings. But that's kind of cool to see that. And then when you want the irradiance, that's 1/2 EP star. When you do the star, all these things with the I flip signs, and when you multiply them, it's going to be 1. It's going to be 1. So I'm going to have here a 1/2. I'll have a 2CA, that's going to be squared. And then I'm going to have a cosine squared alpha sine squared beta over beta squared. And really, I want to get this in terms of the I naught again. So when the theta goes to 0, alpha is 0 and beta is 0, right? Because remember, this is your Ka sine of theta over 2, and this is Kb sine of theta over 2. So when the thetas are 0, beta is 0, alpha is 0. But I know that when that happens, this becomes 1, and this becomes 1. So I'm good. That means I have the I naught out in front. So I'm finished. I'm finished. This means that the I function of theta is I naught cosine squared alpha sine squared beta over beta squared. I got it. That's it. Double slit, interference, diffraction. Interference, see, interference and diffraction kind of go together in a sense here. When you get both, you get factors here. When you did your single slit, you had interference effects with the baby waves. So now let's look at this. This beautiful equation here. We're trying to understand here the I naught, the cosine squared alpha, the sine squared beta over beta squared. So let's look at this. Cosine squared alpha, that's going to be this faint one in the back. So you remember cosine is going to be 1 at 0, and then since you're squaring it, like everything's above the axis. So there's your cosine. So cosine would do this, but you're basically squaring it. So that comes up, so you have all these peaks up there. Now the sinc squared, that would be the dash one. I'm going to call that one the diffraction one, since that depends on the individual slits, the B. And the A that goes with the alpha is the distance between the two, which initially, if you recall, when I did that one, that was what I called interference. So this is called interference. I call that interference. This is like the A, the distance between the slits, the center of the slits, and this is the B. I call that the diffraction. So that means here, we call this the interference one, and that's the diffraction one, even though there's interference with the baby waves in there. But we just think of that as single slit diffraction, and then here you have the interference of the two slits. You have to multiply the dashed one with the light one to get the final result, which is the solid one here. Notice that you can be dead in two ways. You can be dead when the interference term goes to 0. That would be these faint ones. See, when that's 0, we're dead, we're 0. When that's 1, we're dead, we're 0. We're 0, dead. But you could also be dead if this one kicks off. Well, that would be the dashed one. See, well, there you go. See, look, that just knocked off one of this one. This would have been a max. This would have been a max here, but look, since the sync one is knocks it out. It's like gone. It's gone. And that's called missing orders, that we missed an order. These would be considered orders. So here's a diagram labeled. This is a nice diagram here labeled. M equals 1, M equals 2, M equals 3, M equals 4. These are your max that you would have with just due to the cosine alpha. And then because of the product and the sinc squared function killing some off, we call those missing orders, that miss the third order. So this is nice. The faint one in the back, the purple one, is your interference. The two-slit effect, the interference. The diffraction is the blue one. That's your sinc function squared. And then together, like, that's what you get. Beautiful. And here is the real deal. Single slit. So you have your max in the center, you have a minimum, and then here another max. And then here with the double slit, you can think of your cosine part in there, your strong interference effects, see, those dots, but then every now and then an order is missing. And they get shaped. They also get shaped. They're not equally bright because they get shaped, see, in a sense tempered by the sinc squared function. So these peaks, see, get less and less, and then some are missing. So here, the brightest one in the center, they get less and less, and then some are missing. Very nice. Nice physics. Beautiful.